Hey guys, Ms. Peterson here, and welcome to AP Chemistry Lecture 5-1, all about reaction rates. In this lecture, we're going to be talking about collision theories, different ways to increase the rate of a reaction, reaction energy profiles, which you might have heard called potential energy diagrams, and a little bit about catalysts. This corresponds to AP Chemistry topics 5.1, 5.5, and 5.6, and you can find more information in your Brown-LeMay textbook in sections 14.1 and 14.2. So, why do chemical reactions happen? How do they actually happen? That's explained by something called collision theory. And this is pretty intuitive. In order for two reactants, two chemicals to react, they have to interact. They have to bump into each other, okay? But it's not just enough to bump into each other. There has to be two conditions. They have to collide in the right orientation and with enough energy, okay? If those two conditions aren't met, the reaction's not going to happen. For example, if we look at this particulate diagram right here, okay, this is showing a reaction between NO3 and carbon monoxide, color just changed there mid-writing, okay, to produce NO2 and carbon dioxide, okay? If they collide slowly, no reaction is going to happen. They're just going to bounce off of each other. If they're not facing the right way, say if the O is bumping into other oxygen molecules, well, they're not the ones that need to react. The O needs to bond to a carbon. That carbon has to be there to steal it. So if they don't collide in the right orientation, you're also not going to see a chemical reaction, okay? Now, this also is affected by the phase of the chemicals that we're talking about. So sometimes, especially when we're talking about catalysts and stuff, we'll talk about homogeneous reactions versus heterogeneous or heterogeneous reactions. Basically, if everything's in the same phase, then we don't need to consider it too much, okay? If all the reactants and products are in the same phase, then it's just those collision theories. But if you have different phases, say you have a solid on the bottom and a gas reacting, well, that does affect it because now only certain molecules have surface available for those collisions to take place. So those will also be talked about, okay? And when we're talking about this, we will often quantify it with a reaction energy profile. So let me show you kind of what these are. So this is the PhET simulation on reactions and rates. Here we have a reaction, A reacting with BC to produce A, B, and C. Now, if I put some energy into it and I let these bounce, notice they're just going to bounce off of each other, okay? This right here is the reaction energy profile. On the left side, we have the reactants, and on the right side, we have the products. And this green line corresponds to the energy of the system right now. So I'm going to go ahead and reload the launcher, and I'm going to give it enough energy to meet that energy of the products, okay? But you'll notice there is still no reaction happening, okay? They're still just bouncing off of each other. You need to get an even higher amount of energy. That is called the activation energy. If I take that green line up over that blue bump in our potential energy diagram, now we get that reaction happening. Now this one is a reversible reaction, so you can see it going in both ways, but I want to pause for a second. This gray line shows you the progress of the reaction, okay? We're still on the reactants. We have A and B, C. And I'm going to just step this over until we get to that highest energy arrangement. The highest energy arrangement where we have all three atoms involved, all touching, all connected, that's called the activated complex. And that is what needs to happen in order for it to go the other direction. And oh, that time it just formed the products. It must have lost some energy. If I raise up that temperature, give it a little bit more energy in, we should be able to get it. There we go. Okay, cool. Okay, cool. And also note, if I do an angled shot and say I move this around, give it plenty of energy, it still might take a while. Well, it has to find that, but it still might take a while for that reaction to happen. Okay, it has to hit it in just the right orientation. Notice that one, it just bounced off the side of it. Okay, and you can picture this with tons of reactants moving around. Only some reactions are going to lead to successful collisions. Okay, so this is what we were looking at. Now, the potential energy, which is on that y-axis, this is actually a quantified of the bond energy of the reactants or products. Okay, when we get into our thermodynamics, we will be actually calculating that for different compounds, but just know for right now that it is the bond energy. Okay, that activated complex was what I showed you when all of the reactants are touching.
Yeah, go ahead. Either that or a little bit of popcorn.
Okay, so in the middle of being a reactant and being a product. This E sub A is the activation energy, okay? Those are that is the energy needed to cause a successful reaction. Okay, how much energy you have to put into the reactants in order for that successful collision to occur. Okay, and this delta H right here, this is called the reaction energy. It is the change in energy between the reactants. Okay, you can see that line here, and the products. Now, in this reaction, this delta H is going to be negative. A negative delta H means that we have an exothermic reaction. The reaction releases energy. Where if we have a positive delta H, if the products have more energy than the reactants, that's going to be an endothermic reaction. Okay, cool. Okay, cool. Now, we talk about energy a lot related to temperature, and the activation energy is definitely related to the temperature. But remember Maxwell-Boltzmann distributions? Okay, not all reactions are going to have enough energy. Okay, just like not all atoms have the same amount of energy. If we have, say this here, we have some hot particles and some colder particles, different temperatures, the activation energy may be somewhere over here. So you can see that a higher proportion of the warm molecules have enough energy to form those successful collisions. Okay, that's why raising the temperature often increases the rate of a chemical reaction, because you have more molecules moving faster, thus more of them will have enough energy to overcome that activation energy. So, how do we increase the rate of a chemical reaction? Couple different ways, okay? The first easiest way is we need to get those particles closer together. And there's two ways to do that. We could decrease the reaction volume. In chemistry, most of our reactions occur in solution. So if we decrease the volume of the reaction, that's going to increase the concentration of our reactants and thus make the reaction happen faster. We could also just increase the number of moles of the reactants. That will also increase the concentration. Okay. Other option, like we saw with those Maxwell-Boltzmann, we can increase the temperature. That increases the average kinetic energy of the particles, aka increases the speed, so more of them will have that activation energy when they collide. Now, if we're talking about solutions and stuff, we could also break up large particles. And by that I mean like clumps, okay? Maybe a better word for that would be clumps. That increases the surface area. Now, if you have more molecules available, you have more ways for that chemical reaction to form. Okay? And we know this too. We know that when you are trying to get something to dissolve, you got to mix it up. That's another way to increase the rate of a chemical reaction. Or like the sugar, like granulated sugar dissolves faster than a sugar cube. Okay? Similar idea. Ways to increase dissolving is also ways to increase the rate of a reaction. There is one other one though. We could add something to help a reaction along, and that is called a catalyst. Now, there are lots of different ways that catalysts work, okay? But they always increase the rate of a chemical reaction without actually being involved in the reaction. They're not consumed in the reaction. They may be a surface catalyst that just helps orient those two molecules and get them to where they need to be. They might be an enzyme catalyst that binds to the reactants and allows it to be in that proper orientation to react with the products and then lets it go. The easiest reaction to think of for that kind of catalyst is to take a deep breath. Now that chemical reaction that gets the oxygen from your lungs to your blood cells is a enzyme reaction, okay? The oxygen binds to your hemoglobin molecule, which serves as a catalyst to like get it there and take it to where it needs to go, where it is then released. So kind of an intermediary, but your hemoglobin doesn't get used up in that reaction, just the oxygen when it goes to your cells and does all of the things that oxygen does. And anytime a catalyst is used, we call that catalysis. Way you'll see that represented in a reaction energy profile is like this. So we have that 25 joules. That is the activation energy for the uncatalyzed reaction. Uncatalyzed reaction, okay? Where if we add a catalyst, that lowers the activation energy, okay? That is the catalyzed reaction, okay? And then this 15 kilojoules, that is the change in energy of the reaction. So this is another exothermic one. So how do we even measure the rate of a chemical reaction? Well, it's just how much reactants and products you have, that change in concentration, okay? Remember, square brackets often mean molarity, and that is how we represent our rates of reaction. So the change in the concentration over some amount of time, okay? Now, it could be measured as a decrease in the reaction concentration or as an increase in the product concentration, okay? Both of those are used. Most of the time, though, we do focus on the reactants. And just like if someone's running a race, there are different speeds you can measure, there are different rates you can measure. When we're looking at a chemical reaction, there is different rates we can measure. We can look at the average rate of the reaction. On average, how long did it take for all of the hydrogen peroxide to decompose, for all of that iron to rest, okay? We could look at the instantaneous rate. How fast is that chemical reaction going at a single instant in time? Or we can look at the initial rate. As soon as we start that chemical reaction, how fast is it going? And this is used a lot in our kinetics experiments. We'll actually be doing a lab looking at those initial rates of reaction or instantaneous rates. We'll probably do both. Let's look at an example though. Okay, so here we have the reaction between C4H9Cl reacting with water to produce C4H9OH and hydrochloric acid, HCl. Now, they measured at different times the concentration of that reactant species. And you can see that represented in the data table here and in the graph here. Now, to get the rate, the molarity per second, the change in concentration per second, you can just look at it between each two. It looks like they did it over in 50-second increments to get that average rate. And what you might notice in the data table here and in the graph here is that it is not like straight linear. The concentration isn't decreasing by the same amount each time. Rather, that rate is slowing down. Okay, we have that initial rate, the rate at time equals 0 seconds. We could also get at time equals like 600 seconds, draw a tangent line, take the integral, derivative, and find the rate at those seconds to get the instantaneous rate. Or we could just do final minus initial over the total time to get the average rate. But my question for you guys first is, why does the reaction slow down as it progresses? What do you think? Well, we just saw in our rates of reactions that concentration has a big effect on the reaction rate. So as the reaction progresses, the concentration is decreasing. And as the concentration decreases, the reaction rate slows down. Okay, cool? Okay, cool. Now, how do we even measure that though? How do we measure that change in the reaction? Well, there's a lot of different ways that we can do that. If one of the reactants or products, not concentrations, has a color to it, we can use spectroscopy. Okay, we can use a spectrometer like we did with the Beer-Lambert law to find how that concentration is changing. If the reaction produces a gas, we can measure the amount of a gas produced. If it produces a precipitate, we could look at the mass of the precipitate over time. We could also use things like pH meters to look if there's an acid-base reaction going on, conductivity probes if it is an electrolyte turning to a non-electrolyte that conducts electricity, things like that. And like most things in science, we look at it doing a graph. So I want you to look at this graph right here. Okay, we have a particular diagram of A turning into B. We start with 50 molecules of A and we end with 50 molecules of B. What you might notice is that after a little less than 10 seconds, you have the concentrations being equal, and it looks like it takes about that 10 seconds for 50% of that B to decompose, okay? Or 50% of that A to decompose if it's a decomposition, or to turn into that B. Now, could you also figure out the coefficients of the reaction from this? Is it for every 1 molecule of A, I get 1 molecule of B? Yeah. Okay, I started with 50A of A and I ended with 50 of B. That tells me that it's a 1-to-1 ratio. For every 1 molecule of A that dissolved, that reacted, I got 1 molecule of B. So we can tell a lot from looking at those reaction rates. So that reaction, very simply, was A turning into B. It has that 1-to-1 ratio, and yeah. Okay. We could look at the initial rate if we wanted. We know that in the first 10 seconds, about 50% of it decomposed. So 50 over 10, that gives us an initial rate during the first 10 seconds of about 5 molecules per second, if we're looking at it in molecules. Now, to get the instantaneous rate of a reaction, we would have to find the slope of the curve at that point. Now, there are a couple different ways you can do this. If you have taken calculus and you know how to find derivatives on your calculator, from data you can graph it and find the derivative, or you can always do it by finding the slope of a line tangent to that curve. For example, if we wanted the rate of change of A at 20 seconds, I could get in here and try to sketch a line. Let me see if I can do it this way. See, adjust that so it just barely touches that line and is equidistant from the two sides of it. Okay, let's get it as perfect as we can here. Oh, too far over that way. Right slope though, it looks like. There we go. And let's see if we can find the slope of it from that. A little review back to math class. Slope is the rise over the run. So you got to do that little triangle thing. Okay, I'm going to look at it right there. Of course, this is not very precise, but hopefully we can get a sense of that scale. I'm going to go at 10 and 22, so 12 seconds. And it went from 20 to 10, trying to make that easy. So we have the change in the concentration of A would be 10 molecules. Okay. Normally it'll be molarity, but for this, our y-axis is molecules over 12 seconds, giving us a rate of 0.83 molecules per second. Yep. And we can see in the first one, it went from 50 down to 25, so 25 over 10, which was at 2.5 molecules per second. So this reaction slowed down quite a bit between that 10 and 20 seconds. In our next lecture, we'll learn how to write rate laws and quantify all of these. But yeah, that's reaction rates. Okay, cool. Okay, cool.